Hey there guys, Unit 4 is all about naming, or nomenclature. We're going to break this down into 3 separate sections: ionic naming, acids, which are a version of ionic naming, and then molecular naming. I'm going to try to put this together in one big video, but I'll let you know when we're switching gears so that you can take a break if you need to. So nomenclature, by the way, nomen, you might recognize from words like nombre. Different languages have the same root. Basically just means naming. So we're going to learn how to name molecules today. I'm going to start with ionic compounds. So just a quick recap about which compounds would fall in this category. These would be the type of atoms that transfer electrons. So the things that transfer electrons would be a compound that has part metal and part nonmetal, like sodium chloride. The sodium would give up an electron, the chlorine would gain it. This would be an ionic bond. So if you can tell that you have an ionic bond, the next thing that we need to do is name the formula unit. So this may be a new vocabulary word here. Formula unit is just a fancy way of saying the formula for an ionic bond. Sorry, getting tongue-tied today. So let's start with some basic naming rules for ionic compounds. When you name a compound, you always start with the cation. Same with the formula. You always write the cation first, and then the anion would come next. So let's first talk about the cation. You only name the atom. You don't change the ending. You'll see with the anions, we are going to have some different endings. Cations do not change their ending. So if the sodium turns into a sodium ion, we still call it the sodium ion. If calcium turns into a calcium ion, it's still just called calcium. So notice, like with sodium chloride, the sodium part of the name didn't change anything. It's sodium, whether it's an atom or part of the ionic compound. There's one section of the periodic table, however, where you do have to worry about the name of the cation, and that is our transition metals. So we've mentioned that they have a habit of being kind of special, so that's going to be true with the name as well. Transition metals don't have one set charge. We learned when we made formula units that the charge kind of dictates the subscript. Well, how do we know what the charge is on something like a transition metal? Because they have multiple options. So the idea is that you would use Roman numeral. So if you wrote iron 2, that would be the 2+ ion. Whereas if you wrote iron 3, that would be the 3+ ion. And for any transition metal, lead, actually tin and lead are 2 exceptions I should mention. They're in group 4 of the periodic table, or column 14, I should say. And so with having 4 valence electrons, they don't have a strong preference about whether they're going to gain or lose electrons. But knowing that they're metals, we know that they should be losing electrons. The catch is that they don't necessarily lose 4 all the time. They actually act like transition metals. So with tin and lead, we're also going to give them Roman numerals. So in this case, lead 2 would be Pb2+, and then lead with the Roman numeral of 4 would indicate lead 4, so a Pb4+. So you always want to include the Roman numerals in the name of the compound, not in the formula. So this is a common mistake I see too. Once we start going over the Roman numerals, they start appearing in the formula units. Remember when we did Unit 3, we didn't talk about Roman numerals. So if you're writing the symbols and putting them together to make the compound and neutralizing the charges, I shouldn't be seeing the Roman numerals. This is just for the naming. All right, so let's try one. We've got iron bonded to oxygen. So the first thing that I need to do is figure out the charge on the iron so I know what the Roman numeral is going to be. So it's going to be dependent on the oxygen charge. We know that oxygen has a -2 charge, and we know the entire compound is supposed to be neutral. So then what would the iron need to be in order to cancel out the oxygen charge and become neutral? +2. That +2 can cancel with the -2 to make the neutral molecule. So when we name it, we are going to write out the name of Fe, or iron. We're going to write the 2 as a Roman numeral in parentheses, and then we'll finish with oxygen, which, as we'll talk about in a minute, is actually going to change to oxide. So FeO would be named iron 2 oxide. Here we go, iron 2 oxide. So let's try one with a polyatomic ion. You should know your charges for your polyatomic ions because we've memorized that guy. That's our phosphate with a -3 charge. So then what would iron need to be to neutralize a -3 charge? Iron would need to be a +3. I almost wrote the Roman numeral. +3. So now I know that iron needs a Roman numeral of 3. So now it's time to write that. Iron, parentheses 3, and then again, it'll be oxide. Oh no, wait, we're not. We're doing phosphate now. Iron 3 phosphate. All right, and we're going to talk about the endings of these things, these anions, in just a minute. So the point here is that the iron gets a Roman numeral, one of our transition metals, as you write the cation name. Iron 3, and then our anion. Or in the first example, iron 2, and then our anion. Only the transition metals need Roman numerals because the other atoms have set charges. To take this one step further, if you think you get the hang of this, let me give you one more catch here. There are 3 transition metals that have set charges: zinc, cadmium, and gold. Zinc, cadmium, and silver. Those 3, since they also have set charges, don't necessarily need Roman numerals. The point of a Roman numeral is to give the charge for something that could have multiple charges. So you'll only need them for most for most transition metals and tin and lead. All right, let's talk about that anion. So you've kind of seen that it can have different endings. If you have a single type of atom, you would end it with IDE. So before, where we had FeO, the anion was just the oxygen, and so we would end that with just IDE, iron 2 oxide. It doesn't matter if you have multiple of the anions. So even for the iron 4 oxide, we are still just going to end it with IDE, oxide, whether it's 1, 2, or 17 of the anions. If it's the same type of atom, you end it with IDE. So for example, chlorine would become chloride, oxygen would become oxide. So you change the ending to IDE as long as it's not polyatomic. Now, if it is polyatomic, you actually have a few different endings we might use. So we've talked before about how we kind of need to protect them in parentheses and treat them like one whole unit when we balance their charges, because that charge acts on the entire polyatomic ion. So when you name them, you go based on what you have memorized. If you notice the things to know and love list of polyatomic ions, aside from hydroxide and cyanide, the rest of them that have the oxygens all end in ATE. We did that on purpose. So if you see phosphate or nitrate, or sulfate, you just keep it named ATE if you see that exact setup. But if the oxygens are different, the name is different. So when you see the exact polyatomic ion, that is ATE. There's another version of the polyatomic ions that would be just slightly different from what you memorized, which ends in ITE. But which one's which? So it all has to do with the number of oxygens. ATE has exactly one more oxygen than ITE. So for example, phosphate would end with 4 oxygens in an ATE ending. But if I wanted to make phosphite, I would have 1 less oxygen, or 3 oxygens. 3 oxygens, ITE. Notice the charge is still the same. Literally the only difference here is the ending changing to ITE when you have 1 less oxygen. Nothing else changes. So let's look at a few examples. If I had sulfate, SO4, sulfite would be SO3. Notice the 2 minus charge on both of them. Stays the same. If I looked at nitrate, nitrate has 3 oxygens and a 1 minus charge, so nitrite would have 1 less oxygen, NO2, but still have the 1 minus charge. NO2 minus would be nitrite. Chlorate, ending with 3 oxygens and a negative charge. To make chlorite, you would have 2 oxygens and the negative charge. Literally only dropping 1 oxygen and nothing else. So that's going to take you from 8 to 8. So you may have noticed that some of those polyatomic ions on your list have 4 oxygens, some of them have 3. 8 and ite have no correlation to 4 and 3. You just have to memorize a set of ATE ions and then know that you would remove an oxygen to get to the ITE ions. There is a way to expand this process too. Actually, I'm going to use sulfate as an example. So sulfate was SO4 2-, and then to make sulfite, ITE, you would go from SO4 to SO3, and then still have the 2- charge. But what if I had even one less oxygen? So there's actually a prefix that means less or low. So we can put that prefix on sulfite, hyposulfate, to get to SO2-. There's also a prefix that means more oxygen. So that would be per. So if I had per sulfate, again, notice I have more than 8, so I'm keeping the A. That would be SO5 2-. You may have heard the prefix per, such as hydrogen peroxide, where water would be H2O, hydrogen peroxide would be H2O2, more oxygen. So we can also use that for per sulfate, SO5 2-. So these are all the different variations we could have of our sulfate ion. To make it a molecule, we would need to bond it with still a cation, and then we could have the cation and one of these anions, and that would be our formula unit when they come together. So we're just talking about the anions here, just to be clear. These are our options. All right. So let's try some. We've got the names here, 3 of them that give you the name, and you're trying to find the formula unit, or the formula, basically. And then we were given the formula, and then we have to name those molecules. So let's give those a shot. All right, so for magnesium, that would be Mg and would have a +2 charge. And sulfate would be SO4 with a -2 charge. And we want to make sure those charges cancel. So +2 and -2 do cancel. So I don't need any subscripts. If you crisscrossed them, you would get a 2 for each one. But remember that you're supposed to have the lowest ratio. So you would then reduce that to a 1-to-1 ratio. So let me just bake these a little closer together. The formula unit would simply be MgSO4. Aluminum, Al, has a +3 charge, and sulfide would have a -2 charge. The IDE indicates it's the single type of atom, which is how I knew it was just regular sulfur as opposed to sulfate or sulfite. It's not polyatomic when you end in IDE. Now we would want to balance these charges, so we're going to crisscross. We'll bring the 3 down to the S, and we'll bring the 2 down to the aluminum. So let me rewrite this here. We've got Al2, S3. All right, last one going this direction. Calcium, Ca, has a +2 charge, and chlorate, ClO3, perchlorate ClO4. So chlorate ClO3 would have a -1 charge. But to balance the +2 charge, I'm going to need 2 chlorates to crisscross. So let me go ahead and put that in parentheses and put the 2 on the outside. So basically, going from name to formula, you want to identify your atom or polyatomic ion with its charge, and then do your crisscross. If you end up with something that reduces, always reduce it. Now let's go the other way. For lithium, the cation, I am just going to write out lithium. I'm not going to change the ending. And then for PO4, I've got to figure out if 4 was one of the things to know and love. Is phosphate PO4? And the answer is yes. So I'm just going to name this phosphate. So lithium phosphate, done. Now let's look at Ba3N2. So first Ba is barium. It's not a transition metal, so I don't need a Roman numeral. Then I'm going to look at the nitrogen. I have a single type of atom. Even though there's two of them, I don't have a polyatomic ion. I don't have a set of atoms. So this is just going to be nitride, IDE. Last one, aluminum, and then NO2. So aluminum, again, not a transition metal, so all I need to worry about is writing aluminum down. No ending change, no Roman numeral. Now I want to look at NO2. Is NO2 what we memorized? No, it should be NO3, nitrate. So this is one less oxygen, which would make it nitrite with an I, because I have one less oxygen. So you've got to be careful there. If you have less oxygen, it ends in ITE. The normal amount of oxygens would end in ATE. And if it's not polyatomic, it ends in IDE. So the ending here is the trickiest part. The only thing you got to watch out for with the cations is those Roman numerals. So here's our examples for our ionic bonds. There we go. Nice and pretty for you. So now let's move on to acid naming. Acids actually are a type of ionic compound, but they're a special type. With acids, the cation is always hydrogen, or H+. So this would be the hydrogen ion attached to some anion. Now this anion can be just a single atom, like HCl, or it could be a polyatomic ion, like HNO3. Any type of anion where H is in front of the molecule is going to make it an acid. That means that those H's would be given off when they dissolved in water. So to name an acid, you really have to know what the ending was before the anion bonded to the H. So it all has to do with whether it's an IDE, ATE, or ITE type of anion. So the ones that ended in IDE, if you remember, had a single type of atom. So like sulfide would just be the sulfur. When you notice that, the first thing that you're going to do is put hydro in front of the name. And then you're going to change the ending. Instead of using IDE, you're going to use IC. So you may be familiar with hydrochloric acid, a very common acid. So notice it would just be HCl, one type, IDE normally, chloride. We're going to change that to hydrochloric. So using hydro and using ic, instead of calling it chloride, we call it hydrochloric. The other thing you might have noticed if you've heard of acids before is that the name actually usually ends or always ends with the word acid. It's almost a safety thing. We want to make sure everybody knows it's an acid. So we're going to put that on the end of the name. So it's not just hydrochloric, it's hydrochloric acid. So that's our first example here, hydrochloric acid. You also can see the same thing with hydrobromic acid. So this would normally be bromide. You're going to take off the IDE and use IC instead, and tack on the prefix hydro in the beginning. Hydrofluoric acid, same thing. Fluoride, change the ending to IC, and then add the prefix hydro. The next one is a little bit weird, so let's do this together. It is HCN. What is the CN anion? That would normally be cyanide. Although it's polyatomic, it does end in IDE. The acid rules are only based on what it was named before. What is the anion named? So polyatomic or not, cyanide ends in IDE. It's going to follow this set of rules. So instead of IDE, we'll use IC, and we're going to include hydro. Hydrocyanic, and then don't forget the word acid. So cyanide in an acidic bond, or an ionic bond here with the hydrogen, would form hydrocyanic acid. Add hydro, change it to IC, and then add the word acid. Of all the different types of acid naming we're going to talk about, this is the only one that includes the prefix hydro. What this does is it makes the name longer for the smallest elements. The next two types we'll talk about usually involve the polyatomic ions when they end in ATE or ITE, and they're not going to have this hydro prefix, which means the bigger molecules will actually have the smaller names. So let's try those out. Let's look at when it ends in ATE. So this would be the normal amount of hydrogens. If it ends in ATE, it's one of our things to know and love. No prefix, that's what I was just describing. Only the single type of atom, or the IDE, is going to end with or have the prefix of hydro. So no hydro here, but the catch is you're still going to end in IC. So the ATE versus the ITE is the trickiest part because they both end in IC. You've got to be careful. The only difference really is the prefix. You put the hydro on the smaller atoms. Still ending with the word acid as well. So let's look at a few examples. Here's our sulfate ion. Instead of ATE, we're going to use the IC. Sulfur and phosphorus actually add a pronunciation syllable, which is not something I'm super worried about right now. But notice that we have no hydro here. So without the single type of atom, if I have ATE instead, no hydro, just sulfuric acid. This UR is there, again, for pronunciation. Imagine saying sulfic acid. That sounds so weird. So sulfuric acid. The next one also has an extra syllable, our phosphate. So because we have the ATE, we're adding the IC. Notice there's no hydra in the beginning. And then we actually add the OR for pronunciation's sake. So we have phosphoric acid. Next one, our carbonate ion. So carbonate would end in ATE, and so instead of ATE, we're going to use the IC. Notice again, no prefix, just carbonic acid. Let's try nitric acid together. HNO3. So it would be nitrate, but instead of ATE, I'm going to replace that with IC, nitric. Should I have a prefix? Not with the ATE, but I do need to remember the word acid. So HNO3 would be nitric acid. There's our last one. Something else I want to point out while we've got these formulas up here. Notice I have 2 H's versus 3 H's, and even one with only 1 H. How could I tell how many H's? Well, these are ionic bonds. So if I have H, which has a +1, and sulfate, which has a -2, if I crisscross that, I get H2SO4. So the number of H's basically comes from the charge of the polyatomic ion. Phosphate has a -3, so I need 3 H's, and nitrate has a -1, so I only need 1 H. So basically, you're just finding the formula unit if you're asked to go backwards. All right, last version for acids, we have our ITE. So with the ITE, you're going to have 1 less oxygen. If you notice that you have less oxygen than you memorized, you have the ITE polyatomic ion, and the name of the acid is also going to change. Anytime you have a polyatomic ion, you're going to skip the prefix. So that part's still the same. But we're going to have another ending now. We've kind of ran out of endings. We need to change this up a little bit. So the ending for the polyatomic ion here is OUS. So instead of ending with IC, like hydrochloric acid or chloric acid, we'll now have chlorous acid, ending with OUS, but we'll still have the word acid. So let's try or look at a couple together. So notice I have SO3, 1 less oxygen than sulfate. So this would be sulfite, which means the ending will be OUS to replace the ITE. Remember, sulfur and phosphorus have that extra pronunciation syllable. So this will be sulfurous acid. With phosphate, it would be H3PO4, but what if we had PO3? Then we would have phosphite, almost wrote phosphate. And if we have phosphite, that means we're going to change the ending instead of IC to OUS. but we do add in the OR and then have the OUS. Always ending with the word acid. So that would be our phosphorus acid. Same idea with the carbonate. If I have one less oxygen, I would have carbonite. And so that would make carbonous acid. And then with the nitrate, let's do one more together here at the end. HNO3 would be nitrate, but to make it nitrite, I would have one less oxygen, so NO2. So, well, not carbonate, nitrate. So nitrate would be nitrite with one less oxygen. And then to make it an acid, I would change the ITE to OUS. And then what do I want to make sure I don't forget? The word acid. So we've got nitrous acid if it's HNO2. All right. So I think that's probably a good spot to pause it, take a break. We have one last section to do together. We're going to look at the covalent compounds as well. So we'll be right back. Hey guys, we're going to finish up these naming notes with molecular compounds. So molecular actually means something very special. I know we've talked before about how atoms combine to form molecules, but the term molecular, as we move forward, can actually have a very special meaning. Whenever I say molecular, I'm specifically talking about covalent compounds. If I say formula unit, I would be talking about an ionic compound. So there is a difference now that we're in this bonding and naming unit and moving forward too. So molecular compounds, I mentioned, need to be covalent. So that means they're going to share their electrons and be made of all nonmetals. So when I write the molecular formula, I do need to indicate how many of each type of atom there are. When we did ionic compounds, the number was driven by the charge. Remember the crisscross? That meant that the charges would play a role in what the subscripts were, and there was only one way to make the compound neutral. So with the molecular formulas, that's not true. We have CO, carbon monoxide, and CO2, carbon dioxide. The only way to tell them apart by the name is with these little prefixes, like di in carbon dioxide. So that's what we need to add into our naming repertoire, is a set of prefixes in order to use for molecular or covalent compounds. So you are going to keep the atoms in order as you name them. So you're usually going to be given the name and asked to give the formula, or you're given the formula and asked to give the name. So it's not like you have to put them in order for yourself, but there is a reason for why they are in the order they're given. Carbon's usually going to come out to the front most of the time. But even aside from that, say you have a molecule without carbon, you're going to go from lowest electronegativity to highest electronegativity, which basically means you're going from left to right on the periodic table, generally speaking. So just don't jumble the order, know that it is intentional. All right, so about the prefixes. Before I actually tell you what they are, there's one big exception that I want to emphasize. Think back to carbon monoxide and carbon dioxide. How many carbons are there? Well, just one. So why did I say monoxide but not monocarbon? You wouldn't say monocarbon monoxide. Mono is never used on the first atom. It's an exception. Never use mono on the first atom. You can use other prefixes on the first atom, but never mono on the first atom. So here are the prefixes. One, of course, is mono. Then we have di for two, not bi. Bi is used with polyatomic ions, like bicarbonate. Then you would have tri and tetra. So tetra, like tetrahedral, means four. So these first four are the ones that are kind of special in terms of chemistry as opposed to geometry, but then we're going to get into basically geometry prefixes. So we've got penta, hexa, hepta, notice the H, then octa, nona, and deca. And just in case you wanted to be able to name this guy, C6H12O6, you can go beyond deca. This would be dodeca. So there are more prefixes. You're kind of going to add on to the existing prefixes, but these 10 are what you need to know for our honors chem class. All right, so let's look at our molecular suffixes. So suffix would be the ending, right? The nice thing is we're dealing with all nonmetals. That means no ions, no polyatomic ions, no ATE, no ITE. So the only prefix that we need is our IDE prefix. That's all we need to do, is change the very, very end of the word to IDE. You're never going to change the first atom, so that's status quo, right? If you happen to have 3 atoms or more, like with the sugar molecule, you're only still going to change the last atom. So your ending doesn't change for any of the atoms except for the last one. So let's try a couple. So we have carbon and oxygen, but there's 2 oxygens. Since there's only 1 carbon, should I use the prefix for 1 mono? Not on the first atom. So this is just going to be carbon. And then the prefix for 2 is di. So this will be diox. Now that I'm at the end of the word, I'm going to end with IDE. Carbon dioxide. Now let's look at the phosphorus and the oxygen. So I have 2 phosphorus atoms. So should I use the prefix even though it's in the first position? Yes, it's only the mono in the first atom that's the exception. So this would be di-phosphorus. Then we've got our oxygen. Now there's 5 of them, so what was the prefix that meant 5? Penta. And then we have oxide, again using that IDE prefix now that I'm at the end. And going backwards is actually even easier. First look at the atom, nitrogen, then look at the prefix di. And if it's missing, it would be mono, or only one of them. So N2. Now let's do the same thing. Oxide, remember the ending is just changed because it's at the end, so that would refer to oxygen, of course. And then what did tetra mean? 4. So this means I would have 4 oxygen atoms. Now let's look at nitrogen monoxide. So nitrogen is N, and the prefix is missing. So it's missing, that means it's mono, and we don't write the 1 subscript. So that's an understood 1. Now monoxide means 1 oxygen. So I write the oxygen, and then I see I just have 1 of them, and again, that's understood. So this is just NO for nitrogen monoxide. So we have both going from name to formula and formula to name. The prefix just tells you how many of that particular type of atom you have. So you need to be able to go from formula to name and name to formula. So that wraps up our molecular bonding, and with that, our Unit 4 on naming. The next notes you'd be looking for would be on Unit 5. We're going to start getting into something called moles. So I'll see you there.